All right, welcome. In this video, I'm going to go over the solutions to the recitation problems on chapters 22, which is electromagnetic waves, and 27, where we're talking about photons and black body radiation and Wien's law. So the first question here is a question from chapter 27. It says, does a beam of infrared photons always have less energy than a beam of UV photons? And it asks you to explain. And then that's the same question about a single. So does a single photon of IR light always have less energy than a single photon of UV light? And we'll explain. So for question number one, shuffle this around a little bit so that I can write in a way that is more convenient for me. Okay, so does a beam of infrared photons always have less energy? I actually want to answer part B first. So we'll leave A blank for a second. We'll do B first. Okay, a single photon of light follows this relationship. It says E photon. The energy of a single photon is Planck's constant times the frequency of the light. Okay, so a single photon's energy is determined only by the frequency of that light. On the electromagnetic spectrum, the frequency of infrared wavelengths of light is has a small frequency. UV light has a large frequency. And there's a table in your book where you can look up the wavelengths and frequencies of various different things. Remember, if you have the wavelength, you can always know what that means about the frequency and vice versa via this relationship right here. So, right, both of them have the same speed, namely the speed of light, which means that a big frequency is a small wavelength and a small frequency is a big wavelength and vice versa. Okay, so I'm just kind of telling you this, but actually I think on the equation sheet, grab that. I don't have it with me right now, but on the equation sheet on the very last page, there's actually a breakdown, I think, of the wavelengths that correspond to a bunch of different types of light. Okay, so the answer to B is straightforward. Yes, a single photon of infrared light always has less energy than a single photon of UV light. And the reason is because of that equation, okay? Part A is a little bit different. So does a beam of infrared photons always have less energy than a beam of UV light? And the answer to this is no. So I wish I had looked something up before, so I'm going to look it up now, which is the energy of individual photons of light that are infrared and UV. So I'm looking through the book and looking for a table. Okay, well, we're just going to have to make up numbers. So let's just say we'll have an example. I'll make up energies. So let's just say IR has one unit of energy per photon. And UV has, 10 units of energy. Okay, so right, an individual IR has less energy than UV. But if I had a beam of light that had 100 photons of infrared light and only 1 photon of UV light, then there would actually be more overall energy in the IR than there is in the UV. So if my beam has 100 IR photons. That is 1 times 100 equals 100 units of energy. If my beam has 1 UV photon, that is only 10 units of energy, okay? So even though each IR photon has less energy, we have so many more infrared photons than we have UV photons than the infrared beam has more energy. The second question, radio tower emits two 50-watt signals. One is an AM signal at a frequency of 850 kilohertz, and one is an FM signal at a frequency of 85 megahertz. Which signal has more photons per second? This is going to be a more numerical example of what we just did in the first problem. Okay, so let's go ahead and say we have both emits the same power is 50 watts, which is 50 joules per second. The first one is the AM signal is 850 kilohertz, so 850 cycles per second, and our FM signal is 85 megahertz. Let's go ahead and write these just in the units of hertz. So kilo is 10 to the third, so this will be 850,000 hertz. So I'll move the decimal place 3 for this. Mega is 10 to the 6th, so I need to move the decimal place 6 for this. So that's 85 with 6 zeros. Okay, so this is the bigger F by far. Okay, so they have the same total amount of energy, but this AM signal has photons that are way less energetic than the FM signal. So let's go and think about this formula here. Okay, so bigger F means bigger energy per photon. So this, our FM, has more energy per photon. So there's more energy per photon here, and that must mean that we need more of these photons to get up to 50 joules. Okay, let me give you a kind of a more concrete example, kind of following up from what we were doing here. Okay, so right, if there is so let's just say that each one of these has 1 unit of energy. And this is, what is this? Got an extra 2 zeros, so this is 100 units of energy. Okay, so we need to get up to 100 units of energy. We need 100 photons from this AM signal. But we only need 1 photon from this FM signal. Okay, so from this analysis here, I'm going to conclude that the AM signal has more photons. And if I needed to be quantitative, I could even say that the AM signal actually doesn't just have more photons, it has 100 times more photons, because the frequency is 100 times smaller for the AM. Okay, so the AM signal has more photons. So we will go ahead and circle that this is A, so the AM signal has more photons every second. Okay. All right, and the kind of important part and why that worked is that both of them had the same total amount of energy, right? They were both having 50 joules of energy for every second that they were on. And since the AM photons had less energy in each photon, we needed a lot more of the AM photons to get up to that 50 joules. All right, let's do the next one. A typical analog cell phone, we don't have analog cell phones anymore, where they're all digital now, but back in the day when we had analog cell phones, they operated on a frequency of 850 megahertz. A digital cell phone operates on a frequency of 1950 megahertz. What is true about the digital signal? Okay, so let's go ahead and return to the energy per photon is Planck's constant times the frequency. And we'll also throw up here the other equation that keeps popping up from time to time, which says that the speed of light equals its wavelength times its frequency. Okay, so we'll say analog is 850 megahertz and digital is 1950 megahertz. So 1950 is bigger than 850, so this is bigger F. Okay, so we've got a bigger F here, so I'll come over here and I'll say that the digital thing has a bigger F. Everything travels at the same speed, the speed of light. So they have the same C. And that only leaves us with lambda here. If F has to go up, then lambda has to go down in order for them to both have the same speed of light. Okay, so bigger frequency, smaller wavelength. And I've already said that even in this video. Okay, so it must be true that the digital signal has bigger F, smaller wavelength. Okay, so we can cross off A and B. So we know that it's got the digital signal has a shorter wavelength. And now it also will return for the second half of this. We'll say that it has a bigger F. H is a constant, something times 10 to the negative 34, I believe. So this doesn't change. So if the right-hand side of this equation gets bigger, that must mean that the left-hand side of the equation gets bigger. So smaller lambda, and the digital also has more energy per photon. Okay, and that looks like D there. So. Okay, let's do the next one. I have a digital cell phone emits radio waves at a frequency of 1.9 gigahertz. What's the wavelength? What's the energy of individual photons? And how many photons are emitted each second? Okay, so we have that F is 1.9 gigahertz. Giga is 10 to the ninth, so that's 1.9 times 10 to the ninth hertz. The wavelength and energy of individual photons. So for the wavelength, we'll use that the speed of light is the wavelength times the frequency. We know the frequency. We know the speed of light. That's 3 times 10 to the 8th meters per second. That's written on the equation sheet with all the other constants. And we can use that to solve for F. So we'll say that lambda is C over F, which is 3 times 10 to the 8th meters per second, divided by 1.9 times 10 to the 9th hertz. And I didn't get my calculator out, so I'm just going to write down what I have written over here, which is 0.16 meters. 16 centimeters. So that's, I don't know, that far, is the wavelength of the light that your cell phone is operating on. Okay, and what's the energy of individual photons? Say that E photon is H times F. So that is, Planck's constant is 1.26 times 10 to the negative 24th. No, that's not right. I didn't write down Planck's constant. Let's go look it up. 6.2626 times 10 to the negative 34. So 6.626 negative 34 meter squared kilogram per second. It's possible that the unit on your equation sheet is a little bit different than that. It might include joules in it or something like that. But when you boil them all down, they're at their heart the same units. But that's what H is, and F we've already got written down is 1.9 times 10 to the 9th hertz. And this is the number that I just said. So that's 1.26 times 10 to the negative 24. The units here are the units of energy. So if I were kind of following these units, I'd get meter squared kilogram per second squared. A hertz is a 1/2. But it must be that that is what you get when you for a joule. So there we go. So we'll box around that one because that is 2 sig figs. This I only want to be 2 sig figs, so I'll say 1.3 times 10 to the negative 24th joules as my answer to that. And the reason that you turned into this problem is that the second part is harder. So total energy is 0.60 watts. So that is 0.60 joules per second. Okay, so another way of thinking about that is that in 1 second, it's 0.60 joules. Okay, and I find this an easier way to look at it because we're usually more comfortable looking at joules than we are watts. Okay, so well, geez, I have 0.60 joules in 1 second, and I would like to change that to be the units of photons per second. Okay, so a couple of ways that you can think about this. I think that usually most people find it easiest to do this problem by setting up ratios. So let's do that this way. So I've just calculated that I have this many joules per photon. 1.26 times 10 to the negative 24 joules are in one photon. Now we'll set it up as a ratio, right? As long as the units are joules on the top and photons on the bottom, then I can do this. And now I will say that I have equals 0.60 joules in however many photons that I'm looking for. I didn't kind of set this up, and probably the easiest way to solve it, to solve for x, we need to cross multiply and do all of that. But I think hopefully you can see this ratio here, right? There's that many joules in one photon, so there's 0.6 joules in however many photons we're looking for. So if I go through here, I can solve for this, and I'll go x times 1.26 negative 24 equals 0.6 times 1. So I just cross multiplied these two together equal those two together, and now I can divide both sides by 1.26 negative 24, and those will cancel, and I get that x, which is my number of photons. I'm reusing a piece of paper. Nobody ever told me I was going to need to have an entire ream of paper at home, so paper is in short supply at my house, so I have to be careful with how I use it. So x is 0.6 times 1 divided by 1.26 times 10 to the negative 24. And that is 4.8 times 10 to the 23rd photons per second. And I really ran out of space to do that, but that's what it looks like. Okay. And we have one more problem. So let's break out a piece of paper for one problem. what are the wavelength and peak intensity and the corresponding spectral regions for radiating objects at a normal body temperature of 37 degrees Celsius and the temperature of a filament in an incandescent light, which is 1500 degrees Celsius, and the temperature of the sun, which is 5800 Kelvin. Okay, so for this, I think in the class videos, I showed that you can think about the intensity of light that is output from an object. And over here on the y-axis, I'll say the wavelength. Actually, so let's make this a little bit bigger and remind you what we're talking about here. Right, so we can say that, I guess I will write wavelength. Right, so something that is the temperature of the sun right here emits wavelengths at all different wavelengths of light. But this peak right here is the thing that this question is asking for. Okay, so we're just trying to calculate the location of the peak. And as this gets colder, the location of that peak is shifting toward longer wavelengths. So right now my peak is in red, but when I come up to the temperature of the sun, my peak is in these yellow greens. And also this kind of wave, this peak gets smaller, but I can kind of zoom in, turn this 100 into something more like 4. And now you can kind of see as this cools down, the peak is shifting to these longer and longer wavelengths as we cool down. Okay. So to get this back up, in front. Okay. So that's what I want to do. And these problems are super easy. Wien's law says that the wavelength is 2.9 times 10 to the 6th divided by temperature. And in order to use Wien's law, you want the temperature to be in units of Kelvin. And you want the wavelength to be in the units of nanometers. And this is a little different than what we usually do for an equation. Normally, we would never put a wavelength in the unit of nanometers, but we deal in nanometers so much that it's easier to think about nanometers than it is to think about anything else there. So let's go calculate this. I'm checking to make sure that this is, yeah, okay. So for A, I have normal human body temperature of 37 degrees Celsius. Up on the equation sheet, there is a formula that will let you convert from a degree Celsius to Kelvin somewhere. And in order to convert to Kelvin, you add 273 degrees. So we'll do 37 plus 273 gives us 310 Kelvin. So the wavelength is 2.9 times 10 to the 6th divided by 310. And that tells me that this is 9355 nanometers. I'll pull up at the end a figure of what wavelengths correspond to what kind of light so that we can look at that, but let's not do it just yet. For part B, we have the temperature of an incandescent light is 1500 degrees Celsius. And we'll add 273 to that as well to get 1773 Kelvin. So the wavelength is 2.9 to the 6 divided by 1773. And that gives me 1636 nanometers. And doing the same thing for part C, where now we don't need to calculate. We don't need to convert 5800 Kelvin because it's already 5800 Kelvin. I have lambda is 2.66 divided by 5800, which is 500 nanometers. Okay, so now let's look up what kind of radiation that is. And find a good one. That looks good. So here's the wavelength of different kinds of light. And let me zoom in on this a little bit so you can see it a little bit better. I just found this from a Google search because I didn't pull up anything good before I started this video. But you can see this is in nanometers already. So we are good here. And no, we're not in nanometers. Well, 550 nanometers is right here. So 550 nanometers, this is green. And the wavelength of these two things, 900, 930, 55, and these are both wavelengths of infrared. So I needed to pull up a better figure of this, but I think on your equation sheet you have the range of different wavelengths. On the equation sheet, which I have pulled up on a different screen that I can't show you, it says that IR light is 750 to 1 million nanometers. Okay, so this falls in both of these two numbers. Oops. Yeah, both of these two numbers fall in that range, so this is visible light. Okay, and that should do it for this video.